Hey everyone, and welcome back for another deep dive. Today we're going to be tackling something that's foundational to chemistry, but maybe you don't realize how often it's actually used in the real world,
Right.
and that's titration.
Yes.
And we're going to be looking at this presentation called Introduction to Titrations.
Okay.
So, to start us off, titration,
Yeah.
what is that all about?
So titration is this really cool technique we use in chemistry to determine the concentration of a solution.
Yeah.
But the thing is, we don't know what that concentration is. So that's our kind of our analyte.
Right.
But we're going to be using a solution that we know the concentration of.
Okay.
And that's called the titrant.
So we're using the known to find out the unknown.
Exactly.
Okay.
And how we do that is by carefully and very precisely adding the titrant into our analyte.
Okay, so I'm picturing like mixing two solutions very carefully.
Yeah.
Is there more to it than just mixing them together?
Yeah. So the key here is that we're looking for something very specific in this reaction, and it's called the equivalence point.
Okay.
Now, this is the point where the moles of the titrant and the analyte are stoichiometrically equivalent.
Okay, so that's when we know that they've kind of perfectly reacted together.
Yes, exactly.
Okay, so how do we know in the solution that that has happened? Like, what's the visual cue there?
So that's where indicators come in.
Okay.
There's substances that will dramatically change color near the equivalence point.
Interesting.
Yeah, and you can see that with your eyes.
Okay.
But for even more precision, we can actually use a pH meter.
Gotcha. So that's going to give us like a more precise measurement.
Yeah.
Now, I'm kind of curious about these indicators.
Yeah.
How do we choose the right one to use?
Yeah, so the indicator is chosen based on the pH range of where we think the equivalence point is.
Okay.
So, for example, phenolphthalein.
Ooh, that's a fun word.
Yeah, I know that's the tongue twister.
It is.
It changes color around a pH of 8.2.
Okay.
So we'll often use that if we have a strong acid and a strong base that are reacting. But let's say we have a weak acid and a strong base.
Okay.
We might use something different like methyl orange.
Gotcha. So it's all about matching the indicator to the particular reaction that's going on.
Exactly.
So it seems like you need specific equipment to even do this titration.
Yeah.
What are the essentials?
So first off, we need something to actually deliver the titrant really precisely.
Okay.
And for that, we use something called a burette.
A burette.
Yeah, have you seen one of those before?
Yeah, I mean, I've never used one before, but I have seen them in labs.
Yeah, it's like this graduated glass tube, and it has a stopcock at the bottom.
Okay.
And that allows you to add the titrant, like drop by drop.
Very carefully. So it seems like precision is really important here.
Absolutely.
Okay, what else?
So then we have to measure our analyte out, and for that we use a pipette.
Okay.
And then we're going to need something to hold our analyte.
Okay.
And so we're going to be using an Erlenmeyer flask.
Okay.
You know, the one that's kind of conical shaped.
Yes.
Yeah. And the shape of that actually helps prevent splashing.
Oh, very important.
Yeah.
Okay, and I know you mentioned we have to figure out when the endpoint is.
Right.
So we need something for that as well.
Yeah, so for that, we can either use indicators, as we already talked about,
Okay.
or we can use a pH meter.
Right.
And one last thing that's really important is a stir.
Okay. A stir. So that's going to make sure that it's all mixed up.
Exactly.
Okay, so we've got all of our equipment. Walk me through what the process is like. What are the steps?
All right, so the first step is to prepare our analyte solution.
Okay.
And we're going to know the volume of it.
Okay.
And then we're going to fill our burette up with the titrant solution.
Okay.
And we're going to record that initial volume reading.
Gotcha. So we're being very precise right from the start.
Yes, absolutely.
Okay. What's next?
So now we get to the really critical part.
Okay.
We're going to slowly add the titrant to the analyte.
Okay.
And we're talking drop by drop. And as we're doing that, we're going to be swirling the flask to make sure everything's mixing together.
Okay, so what can go wrong in that step?
So one of the most common mistakes is that people add the titrant too quickly,
Okay.
especially when you get near the end.
Okay.
Another one is not mixing thoroughly enough,
Okay.
and then just reading the burette incorrectly can also throw things off.
Gotcha. So there's a lot of places where things can go wrong if you're not careful.
Yeah, definitely got to be precise.
So as we're adding that, what are we looking for?
So we're going to be watching very carefully for the endpoint, and that's either going to be signaled by a change in the color of the indicator,
Okay.
or we'll see a sudden jump on the pH meter.
Gotcha.
And once that happens, we're going to stop adding the titrant.
Okay.
And we're going to record the final volume reading on the burette.
So now we've got our endpoint, we've got all this data.
Yeah.
What do we do with it?
Well, that's where we get to do some fun math.
Okay.
So using that volume of titrant that we used, the known concentration of the titrant, and the stoichiometry of the reaction, we can then calculate the concentration of our analyte. So
we're solving for X, basically.
Exactly.
Cool.
And we can actually visualize this entire process by plotting it on a graph.
Okay.
And it's called the pH titration curve.
Okay. I'm intrigued.
Yeah, so it basically shows you how the pH changes as you add the titrant.
So we can see that reaction happening?
Yeah, you can see the change.
That's pretty cool.
Yeah, it's really neat. And the equivalence point, that really important point we were talking about, it's going to show up on the curve as like a really sharp change.
Okay.
And another really cool thing is that the shape of that curve can actually vary based on the strength of the acid and the base.
Ooh, okay.
But we can talk more about that a little bit later.
Okay. I'm excited to get into that. Now, I know that you mentioned that it's a neutralization reaction.
Yeah.
So can you tell me more about what that means?
So neutralization reactions happen when you have an acid and a base.
Okay.
And they react together.
Okay.
And they produce salt and water.
Okay, so it's almost like they're canceling each other out.
Yeah, and neutralizing each other.
Interesting.
Yeah. And a really neat fact is that most of these reactions are exothermic.
Okay, I'm familiar with that term, but I'm blanking on what it means. Remind me.
Yeah, so exothermic means that heat is released.
Okay, so the solution would get warmer.
Yeah,
Got
yeah. And you've probably seen this in your everyday life.
Really?
Have you ever mixed baking soda and vinegar together?
Oh, yeah.
Yeah, that's a neutralization reaction.
Wow, so that fizzing is a neutralization reaction? That's so cool.
It is.
Okay.
And another interesting point is that if you have a really strong acid and a really strong base,
okay,
the pH at the equivalence point is going to be 7.
Okay.
Which is neutral.
Right, so that makes sense why we call it a neutralization reaction. Okay, I'm curious, though, because, we've been talking about all this theory, but I know that the presentation mentions that there are a lot of applications for this.
Yeah, definitely.
So what are some real-world examples of how titration is used?
Well, one of the most common places you'll see it is in environmental science.
Okay.
Like we already mentioned, determining the alkalinity of water.
Okay, so alkalinity, what is that?
So alkalinity basically tells you how well a solution can neutralize an acid.
Okay, so like if something acidic gets in the water,
right,
how well can the water buffer against that change?
Exactly.
Okay.
And that's really important because if you have water that's too acidic,
okay,
it can harm aquatic life.
Gotcha.
And it can actually corrode things like pipes.
So we need to keep a check on that for a lot of reasons.
Yeah.
Okay, what else?
Another important area that it's used in is agriculture.
Okay.
So farmers actually use titration to monitor the acidity of their soil.
Okay.
And that's important because different plants need different pH ranges to thrive.
So it's like they're testing their soil, and then they know maybe what crops would grow best, or maybe how to amend the soil?
Right, like if they need to add lime or something to kind of adjust the pH.
Interesting.
Yeah. It's also used in the food industry.
Okay.
We mentioned salt before.
Right.
But they'll also use it to measure acidity.
Oh.
So think about things like vinegar.
Okay.
Citrus fruits.
Okay.
Yogurt.
Yeah. I mean, the acidity is definitely part of the flavor of those.
Yeah. It affects the taste.
Okay.
And it affects how well it's preserved.
Gotcha. So you need to get it just right.
Yeah.
Okay. I'm also curious about any pharmaceutical applications.
Yeah. So the pharmaceutical industry uses titration all the time.
Okay.
For example, they use it to analyze the concentration of the active ingredients in a drug.
Oh, so that's really important for making sure that the medicine's going to be safe
Right.
and effective.
Absolutely.
Okay, so we've got, environmental science, agriculture, food, medicine.
Pharmaceuticals, yeah.
Wow, so this is really being used everywhere.
Pretty much, yeah. I mean, there's tons of other examples.
Wow.
It's just a very versatile technique.
So I'm really impressed. This is really cool.
Yeah, it is.
Now, I did want to go back to something that you mentioned earlier.
Yeah.
You said that the strength of the acid or the base can actually affect the shape of the titration curve.
Right.
And I wanted to know more about that.
Okay, so the shape of the curve basically tells us how easily that acid or base will ionize in a solution.
Okay.
So what that means is how easily it loses or gains a proton.
Okay, so like how reactive is it?
Yeah, kind of.
Okay.
So a strong acid will completely ionize when it's in a solution.
Okay.
But a weak acid
That's
is only going to partially ionize.
So it's not as eager to give up that proton?
Yeah.
Yeah.
So this different behavior
Yeah.
leads to different shapes in the curve.
Gotcha. Okay, so
Yeah.
what are those shapes?
Okay, so if you're titrating a strong acid with a strong base,
Okay.
that equivalence point is going to happen at a pH of 7.
Okay.
And the curve is going to be really steep and symmetrical around that point.
Okay.
Um, but if you're titrating a weak acid with a strong base,
Okay.
it's going to be a much less steep curve,
Okay.
and it's not going to be symmetrical.
So it almost seems like the curve is telling us a story about how that reaction is happening.
Yes.
Cool.
Yeah, it is. And it can actually tell us more than just the strength. It can
Absolutely.
tell us more about the nature of the acid and base.
Wow.
Yeah.
Okay, well, this has been so interesting. I feel like I'm learning so much,
Me too.
and I can't wait to learn more in our next episode.
Awesome.
So we've talked a lot about the theory behind titration, but in the real world, when we're using this to, like you said, monitor water or look at pharmaceuticals,
Right.
accuracy is super important.
Yeah, definitely.
So how do we make sure that when we're doing a titration that our results are actually accurate?
Yeah, that's a great question. So it all really starts with just paying attention to detail in every single step. So from preparing the solutions to making sure all of our equipment is calibrated properly,
Okay.
to actually performing the titration itself.
Okay, so there are a lot of pieces to making sure this is done accurately.
Right.
Can you break down some of the specific steps, though, that we need to be thinking about?
Yeah, so one of the most crucial things is making sure that all of our equipment is calibrated properly.
Okay.
So that's especially important for things like the burette and the pipette.
Right, because if we're not starting with accurate tools,
Right.
our results aren't going to be accurate.
Exactly.
Okay, I'm curious about the calibration, though. How often do we need to do that,
Yeah.
and what are we even calibrating against?
So how often you calibrate really depends on how often you're using that piece of equipment.
Okay.
Um, and it also depends on how precise your measurements need to be.
Okay.
So if you're doing like routine titrations, you might calibrate it daily or weekly. But if it's something that needs to be super precise,
Yeah.
you might calibrate it before every single use.
Gotcha.
And we always calibrate against a certified reference material.
Okay.
And that's basically a material that has a very precise and traceable concentration.
So we know exactly what it is.
We know exactly what it is,
Okay.
and we can use that to adjust our equipment to make sure that it's reading correctly.
Gotcha. So we're making sure that our measurements are consistent with this kind of gold standard.
Exactly.
Okay, what about the actual process of titration?
Yeah.
Are there any tips there for making sure it's accurate?
Yeah, so one of the most important things is to go slowly and steadily when you're adding the titrant,
Okay.
especially as you get close to that endpoint.
Okay.
We really want to be adding it drop by drop to make sure we don't go past the equivalence point.
Okay.
And as you're adding the titrant, make sure you're swirling the flask or using that stir.
Okay.
You want to make sure everything is mixing together really well, so that the titrant and the analyte are reacting completely.
So it's like if you're making a cake batter, you want to make sure everything is combined.
Yeah, exactly.
Yeah.
And then another really important thing is making sure you're reading the burette and the pipette correctly.
Okay, so are there specific ways that we should be doing that?
So you always want to read from the bottom of the meniscus.
Okay. I'm going to be honest, I don't know what that word means.
Yeah, so the meniscus is that curve you see at the top of the liquid.
Oh, okay.
Because of surface tension, the liquid kind of curves up at the edges.
Okay.
And the bottom of that curve is the most accurate place to take your reading from.
Gotcha. So it's not just lining up the liquid with the line on
Right.
the side of the tube.
Exactly.
Okay.
And of course, just basic cleanliness is super important.
Okay. Cleanliness. Yeah, I feel like that's kind of a given in a lab.
Right, you would think so.
But what kind of things should we be looking out for, or how should we be cleaning our equipment?
So you really want to make sure that your glassware is spotless.
Okay.
Like there's no residue
Yeah.
from anything that was in it before.
Okay.
Because even a tiny amount can actually throw off your measurements.
Oh, wow. Okay, so it's really that sensitive.
It is.
Okay. What are the best practices then for making sure that our glassware is actually clean?
So typically we'll rinse it really well with distilled water,
Okay.
and then we'll rinse it again with whatever solution we're going to be putting in it.
Okay, so like if we're going to be putting an acid in it,
Yeah.
we'll rinse it with the acid first.
Exactly.
Okay.
And that just helps to minimize the risk of any contamination.
So we're removing anything that could mess up our results.
Exactly.
Are there any other things that we need to keep in mind that could affect the accuracy?
Yeah, so as we talked about before, choosing the right indicator is really important.
Okay.
If you choose the wrong one, it might change color at the wrong pH,
Okay.
and then you won't get an accurate endpoint. Um, and then another simple but really helpful tip is to do multiple trials of the titration.
Okay. I remember doing that in my chemistry class.
Yeah. Yeah.
Why is that so important, though?
So if you do multiple trials and then average the results,
Okay.
that can help to kind of average out any errors that might have happened during any one trial.
Okay, so you're getting a more reliable result.
Exactly.
Now I'm kind of curious about the history of titration.
Oh, yeah.
Like who came up with this technique?
Yeah, so the roots of titration go way back to like the early days of analytical chemistry.
Wow.
But the version that we use today really started to take shape in the 18th century.
Okay. So who were some of the people that were working on this?
So one of the early pioneers was a French chemist named François-Antoine Henri de Croisy.
Wow, that's a mouthful.
I know, right?
Okay.
But in the late 1700s, he developed this early form of titration to measure the alkalinity of potash.
Okay, potash, what is that?
So potash is basically a potassium compound that was used in a lot of different industries back then.
Okay, so it was a practical problem they were trying to solve.
Right. They needed a way to figure out the quality of the potash.
Okay.
So he came up with this really simple apparatus that used a graduated cylinder and a colored indicator
Okay.
to figure out how much acid he needed to neutralize a potash solution.
So it was kind of a rudimentary version of the burette and indicator systems we use today.
Exactly.
That's cool.
Yeah, it is. So then later on, another French chemist named Joseph Louis Gay-Lussac,
Okay.
he came along and he kind of refined Descroisy's method.
Okay.
And he developed a more precise technique that he called volumetry.
Volumetry. I feel like I've heard that before.
Yeah, and it makes sense, right? Because titration is all about measuring volumes.
Right. Yeah, that makes sense.
Yeah, so he introduced the burette, which is like the one we use today.
Wow.
And that made it possible to deliver the titrant more precisely.
So he really helped to kind of bring titration into the modern era. Yeah.
So it went from this like potash analysis to something that we use in all different kinds of fields today.
Yeah, it's amazing, right?
It is. Now, we talked about some real world examples before.
Yeah.
But I want to know more.
Okay.
So what are some other areas where titration is being used that maybe people haven't even thought of?
Yeah. So there are a ton, like it's such a versatile technique
Yeah.
that it's used in so many different fields.
Okay.
So one example is environmental science.
Okay. We talked about water quality.
Yeah.
So what else?
So for example, titration is used to determine the acidity of rainwater.
Oh, okay. Acid rain.
Mhm.
That's a big one.
Yeah, it is.
How are they using titration to do that?
So basically they'll take a sample of rainwater
Okay.
and they'll titrate it with a base solution.
Okay.
And that allows them to measure the concentration of acidic pollutants in the rain,
Okay.
like sulfuric acid and nitric acid.
Oh, so that's the stuff that's causing the acid rain.
Yeah.
Yeah. And those usually come from industrial emissions.
Gotcha. So this is helping them to track that.
Exactly.
Okay, so titration is being used to like monitor the environment. What else?
It's also used in soil analysis.
Okay.
So they can use titration to figure out the cation exchange capacity of soil.
Ooh, cation exchange capacity? I feel like that's a term I've heard before, but I'm blanking.
Yeah, so basically it's a measure of how well the soil can hold on to positively charged nutrients,
Okay.
like calcium, magnesium, and potassium.
Gotcha. And those are important for plants.
Super important.
Okay.
And they're held on the surface of soil particles.
Okay.
And the cation exchange capacity tells you how many of those kind of nutrient binding sites are available.
So how fertile the soil is, basically.
Pretty much.
Okay. How do they use titration to do that?
So basically what they'll do is they'll saturate the soil with a known cation, like ammonium,
Okay.
and then they'll displace those cations with another one, usually sodium. And then by titrating that displaced ammonium, they can figure out how much was originally held by the soil.
Okay, so it's like a before and after.
Yeah.
Okay, that's really cool.
Yeah, it is.
Okay, so we've talked about how titration is helping to protect the environment and to grow food.
Mm-hmm.
What about what we eat?
Yeah.
Are there any applications there?
Oh, yeah, definitely.
I know we talked about salt,
Right.
but what else are they using it for in the food industry?
So one important thing is determining the acidity of different food products.
Okay, so like making sure that the orange juice isn't too sour.
Yeah, exactly.
Okay.
So anything that has like vinegar, citrus fruits, yogurt, the acidity level is really important.
Right, it's part of the flavor.
Yeah, it affects the taste.
Okay.
And it also affects how well it's preserved.
So if it's too acidic, it might spoil faster.
Exactly.
Okay.
So food manufacturers can use titration to make sure that the acidity levels are just right.
Oh. Oh.
And that helps to ensure that the food tastes good and stays fresh longer.
Okay, so it's like a quality control thing.
Yeah.
Now, are there any other applications in the food industry that might surprise people?
So they actually also use it to determine the vitamin C content.
Oh, really?
Yeah.
How do they do that?
So vitamin C is an antioxidant,
Okay.
um, and it can be oxidized by iodine.
Okay.
So what they'll do is they'll titrate the food sample with an iodine solution,
Okay.
and then they'll measure how much of that iodine is used up.
Okay.
And that tells them how much vitamin C was in the sample.
So it's like the vitamin C is reacting with the iodine.
Yeah, exactly.
Okay.
And they can use that to verify the amount of vitamin C that's listed on the label.
Oh, wow, that's really important.
It is.
Okay, so we've got, environmental protection, food production.
Mm-hmm.
What about medicine?
Yeah, so titration is really important in medicine, too.
I know you mentioned it earlier, but can you tell me more?
Yeah. So, for example, it's used to make sure that the medicines we're taking are pure.
Okay. Pure, how so?
So they want to make sure that the drug doesn't have any contaminants in it.
Okay, right. Because that could be dangerous.
Yeah, definitely.
So how are they using titration to do that?
So they'll take a sample of the drug
Okay.
and they'll titrate it with something that reacts with the active ingredient.
Okay.
And that lets them measure how much of that ingredient is present
Okay.
and make sure it's pure.
So they're checking that it's the right concentration.
Right.
Okay, what else?
They also use it to measure the concentration of drugs in our bodies.
Oh, so like in our blood.
Yeah.
Okay.
So that can help doctors to figure out the right dosage of a medication.
Okay.
And to monitor how a patient is responding to treatment.
Okay, so it's a really important tool for doctors.
Yeah.
Okay. What about industry?
Yeah. Titration is also used all over the place in industry.
Okay, I'm ready for some examples.
So one common use is in wastewater treatment.
Okay, wastewater treatment.
Yeah, so they use it to monitor things like the pH, the alkalinity, and the concentration of pollutants in the wastewater.
So it's helping to make sure that it's safe
Right.
before it's released back into the environment.
Exactly.
Oh, okay.
And in manufacturing,
Yep.
they use it to control the concentrations of different reactants in chemical processes.
Okay.
So like for making fertilizers, detergents,
But yeah.
even plastics.
Wow, so this is really being used to make all kinds of things.
Yeah, it is.
I had no idea.
It's pretty cool.
It is. So it seems like titration is really a foundational technique in chemistry.
Absolutely.
And it's being used to solve problems
Yeah.
and to improve our lives in all kinds of ways. Now, I do want to go back to something we talked about before, which was this difference between the equivalence point and the endpoint.
Oh, yeah.
Because I know that sometimes those terms are used kind of interchangeably,
Right.
but I have a feeling they're not exactly the same thing.
Yeah. Yeah, you're right. They're not.
So can you walk me through what that difference is?
Yeah. So the equivalence point, remember, that's the theoretical point.
Okay.
Where the amount of titrant you've added is exactly the amount you need to completely react with the analyte.
Right. So it's like the perfect chemical balance.
Yeah.
Okay.
But it's theoretical.
Right.
So it's not something you can actually see.
Gotcha.
The endpoint
Okay.
is what we actually observe in the lab.
Okay. So it's what we're seeing.
Yeah.
Okay.
So that's the point where we see the indicator change color
Okay.
or the pH meter suddenly jump.
Gotcha.
And that tells us, okay, the reaction is pretty much done.
Okay. So that's when we would stop adding titrant.
Right.
Okay. Now, you said they're not always exactly the same.
Yeah.
Why is that?
So there are a couple of reasons.
Okay. Hmm.
One is the indicator that we're using.
Okay.
Some indicators are more sensitive than others.
Okay.
And they might change color a little bit before or after the actual equivalence point.
So it's like the indicator is a little slow to react.
Kind of, yeah. Another reason is the concentration of the solutions.
Okay.
So if you have really dilute solutions,
Okay.
the change in pH near the equivalence point might not be very sharp.
Okay.
So it can be kind of hard to tell exactly when you've reached the end point.
So it's kind of a judgment call?
Yeah.
Okay.
And then sometimes the reaction itself
Okay.
might take a little bit of time to finish.
Oh, interesting.
Yeah, so even though you might see the indicator change color,
Okay.
the reaction might still be going on for a little bit longer.
So there's a bit of a delay between what we're seeing and
Right.
what's actually happening?
Exactly.
Okay. Now, you said that the difference is usually pretty small, though.
Yeah, it is, especially if you're using the right indicator
Okay.
and you're doing the titration carefully.
Okay. But it's still something we need to keep in mind.
Right. You always want to be aware of the potential sources of error.
Right. We need to make sure that our results are accurate.
Exactly.
Now, I'm curious about something else. Earlier, we were talking about how we can use titration to find the concentration of an unknown solution. But can we also use it to figure out other things about a solution?
Yeah, definitely.
Yeah.
So one really cool thing you can do is use it to find the pKa of a weak acid.
Okay, pKa.
Yeah.
I feel like I remember that from chemistry class, but remind me what it is.
Yeah, so pKa is basically a measure of how strong an acid is,
Okay.
or how easily it gives up its proton.
Okay, so the lower the pKa, the
Yeah.
stronger the acid.
Exactly.
Okay. How does titration help us to find the pKa?
So if you titrate a weak acid with a strong base,
Okay.
you can actually see the pKa on the titration curve.
Oh, really?
Yeah. So remember that halfway point
Okay.
where you've added half the volume of base that you need to get to the equivalence point?
Mm-hmm.
The pH at that point is actually equal to the pKa of the weak acid.
Wait, really?
Yeah, it is.
Okay, why is that?
So at the halfway point, you've neutralized half the weak acid. So you have equal amounts of the acid and its conjugate base in the solution.
Okay, so it's kind of like they're balanced.
Yeah.
Okay.
And the pKa tells you at what pH that balance occurs.
Oh, so that makes sense.
Yeah, it's pretty neat.
It is.
So just by doing a titration and keeping an eye on the pH, you can figure out the pKa of a weak acid.
So it's like another piece of information that we can get from this one technique.
Exactly.
That's really cool.
It is.
Okay, well, this has been so interesting.
It has.
I feel like I've learned so much about titration.
Me too. I always learn something new when we talk about this stuff.
Okay, well, let's keep learning.
Okay.
Okay, so knowing the pKa, like you said, is really important.
Yeah.
But can you give me a specific example of how we might actually use that information?
Yeah. So let's think about drug design.
Okay.
So a lot of drugs are actually weak acids or bases.
Okay.
And the pKa of that drug is going to affect a lot of things.
Like what?
Like how it's absorbed by the body, how it's distributed, and even how it's metabolized.
So that's really important information for the people who are actually designing these drugs.
It is.
So how does knowing the pKa help them to do that?
Okay, so for example, let's say we have a drug that has a pKa
Okay.
that's close to the pH of our stomach.
Okay.
That drug is probably going to be absorbed really well in the stomach.
Okay.
But if it has a different pKa,
Okay.
it might be absorbed better somewhere else, like the intestines.
Okay, so they can actually use that information to design the drug.
Right.
In a way that's going to be the most effective.
Exactly. And it can also help to reduce side effects.
Oh, okay. So it's really important for both of those things.
Yes, yeah.
Now, what about something like environmental science?
Yeah, so in environmental science, knowing the pKa of pollutants can help us to understand how they behave in the environment.
Okay.
So, like how easily they dissolve in water.
Okay.
Whether they bind to soil.
Okay.
Or even how toxic they might be to different organisms.
So it's helping us to understand like the big picture of how that pollutant is going to affect the environment.
Yeah, basically.
Wow. So it's really interesting how this one little number can have such a big impact on so many different things.
Yeah, it is.
Well, I have to say, I'm really impressed with how much we've been able to cover in this deep dive.
Me too.
We've talked about, the basics of titration.
Yeah.
All the different applications, the history, and even how we can use it to understand some really important chemical properties.
Yeah, it's been a really fun deep dive.
It has.
I always enjoy talking about this stuff.
Me too. I feel like I've learned so much.
Yeah, and hopefully our listeners have too.
Yeah, I hope so. Well, thank you so much for joining us on this deep dive into the world of titration.
Thanks for having me.
And we'll see you next time for another deep dive.